We'll go over some questions in thermochemistry. Now, the first question we've been given: how much energy is required to heat 80 grams of water from 26 degrees to 48 degrees? We've been given the specific heat capacity of water. So really, specific heat capacity is the amount of heat energy required to change the temperature of a substance, or to raise the temperature of a substance by 1 degree Celsius, and that substance should be the 1 kg of that substance. And so Q is given by, Q is representing energy, that is mass times specific heat capacity times change in temperature. And so the energy, we want to calculate how much energy. We know the mass of water is 80 grams. Okay, 80 grams. The specific heat capacity, I've decided to use 80 grams without converting to kg because the specific heat capacity has been given also in grams. Specific heat capacity has been given as 4.184 joules per, means we have a gram down and then a degree Celsius down, and then multiplied by the change in temperature. It's coming from 26 to 48, so the change is 48 minus 26, which is 22. So that is times 22 degrees Celsius. Notice that the degree Celsius cancels, the grams also cancels, and so the unit remains in joules. And so therefore the value is going to be 7363.8 joules. So which we can just take to kilojoules. We have got a joule on top, we are going to have a joule down, and then kilojoule on top. Know that in 1 kilojoule I've got 1000 joules. So the decimal point is going to move 3 times. So that would be 7.4 times 10 to the power 3. Okay. Kilojoules. Now there is also this one. So notice that the joule and the joule is going to cancel. And then we are dividing by 10 to the power 3. So the 10 to the power 3 cancels out. So that would be 7.4 just kilojoules. So if that was a little confusing, let me just write it smart simple. Okay. So in this manner. So we are saying this joule and this joule is going to cancel out. And this is going to reverse 10 to the power 3 into this number which you have here. The decimal point is going to remove in that manner, so it will be now 7.3638 kilojoules, which we can simply round off to 7.4 kilojoules. So that is the amount of heat energy then. Next question: how much energy is required to melt 75 grams of ice? The heat of fusion of ice has been given as 334 joules per gram. So melting, we need to understand what heat of fusion is. So heat of fusion is the amount of heat energy that is required to change the temperature, to change the state of a substance. So if you've been given ice is at 0 degrees, so it is here. Now we want to change, how much energy is required to melt. We want to melt this ice. So the only way that this ice is going to become a liquid, because whenever it is, as long as it is at 0 degrees here, it is still ice. So for us to raise it to become a liquid, it first needs to, all the ice has to be converted into water. Okay. So for ice to change state, the energy required for a change of state is called latent heat of fusion. In this case, to change from solid to liquid is latent heat of fusion, which have been given there. So the energy is given by mass times latent heat of fusion. So I want to calculate the energy, but we've been given the mass as 75 grams. Latent heat of fusion as 334 joules per gram. So notice that the grams cancel out, and so that is going to give us 25050 joules, which we can also convert We have got a joule on top, we bring a joule down, and then a kilojoule on top. In 1 kilojoule we have got 1,000 joules. So this will leave, the decimal point is going to move from this point 1, 2, 3. So this will be 25 kilojoules. So this is the amount of heat energy that is required for us to convert 75 grams of ice into water. Okay, in other words, to melt it. Alright, we've been given another question. A 70 grams metal at 180 degrees was put in a bucket containing 400 grams of water at 25 degrees. So what we are having is, we have got a bucket of water. This bucket of water contains water there. Then the mass of water we've been given as 400 grams. And then we put a metal. And then this metal is 70 grams. And we know its temperature. So the metal has come with a temperature of 180. In other words, this metal is hot. And then the water is cold. See, the water is at 25 degrees Celsius. This is at room temperature. So when you add something hot to the water, what is going to happen is the water is going to become hot, and then the metal is going to become cold. So the temperature is going to change. Okay. And then the final temperature of the mixture is now 28 degrees. Notice that it is above 25 but below 180. Okay. So the metal has lost some heat while the water has gained some heat. That is why the mixture has got this temperature. Now what you need to know is that energy is never made or destroyed. It can only be converted. So that means the energy of the water should be equal to the energy of the metal. Now because the metal is losing, we are going to put negative. That is why the temperature has changed from 180 to 25. So this 25 is the final temperature, like the water and the metal, they are all going to be at 28, I mean. So that is why the metal has lost, so we have put a negative in front. So how do you find the heat for water? Heat is given by mc delta T. That is a specific heat. Okay, heat for the water is given by mc delta T, and then heat of the metal is also given by mc delta T. Now the mass of the water has been given as 400 grams. Specific heat capacity for the water of course this is a known value. The specific heat capacity for water is a known value, and that is 4.184 joules per gram degree Celsius. And then the change in temperature, the final temperature is 28. The initial temperature for the water was 25. So the change is 28 minus 25, which is simply 3 degrees Celsius. And that should be equal to negative. The mass now of the metal is 70 grams. Specific heat capacity is what we don't know. And then the change in temperature, it has moved all the way from 180 to the final, which is 28. So there is a decrease, and so the change in temperature is going to be final, which is 28, minus initial, which is 180. So 28 minus 180 is negative 152. So I'm multiplying by negative 152 degrees Celsius. So notice this degree Celsius cancels with this degree Celsius, the gram cancels with this gram. So if we multiply the first portion, 400 multiplied by 4.184, then multiplied by 3. So this portion will give us 50,208 joules, and that is going to be equal to the other side, 70 grams multiplied by negative 150. Remember, this is already a negative. Multiplied by another negative which is inside there, it becomes positive. So that will be 70 times 152. It is 10,640. So this is in grams, and then degrees Celsius, and then now we have got a specific heat capacity there. So this grams is coming from the water, this degrees Celsius is coming from there, from the temperature, and then we have got the C, which is we've put there. So we're going to divide by 1064 gram degrees Celsius, even this side 10640 gram degrees Celsius. So the specific heat capacity then is going to remain as 50208 divided by 10640. So that is 4.71 joules per, we can see these which are down, per gram degree Celsius. So that becomes then the specific heat capacity. Okay, let me again repunch on the calculator. Perhaps I've used a wrong punching. So we are saying 400 multiplied by 4.184 and then multiplied by 3. Okay, and then we are dividing that by the product of 70 and 152. 70 times 152. Okay, so there was wrong with my punching on the calculator. So that value is supposed to give us, let me just start from this point. So of course 400 multiplied by 4.184 and then multiplied by 3, that gave 50208. Then the other side 70 multiplied by 152, 10640, and then times the C, which we don't know is there. So to remain with C, 5208 divided by 106. Okay, so that is supposed to be 50208 divided by 10640. I'm still finding the same answer, which is so different. Maybe 400 times 4.184 times the 3, 50. Okay, there was a point, so I was leaving out a point there. That is why I was finding different answer. Okay, so the answer is 0.472 joules per gram degree Celsius. So that becomes the value then. Okay, another question given: a 30 grams of iron at 95 degrees Celsius was placed in a 20 grams water at 25 degrees Celsius. What is the final temperature? So same here, notice that iron was first at 95 and then we pressed it in water at 25. So the iron is hot, the water is cold. That means the iron is going to lose some of its temperature to give to the water, and then they are going to have the same final temperature. So what we are saying is energy of the iron, let's start with the water, is going to be equal to negative energy of the iron. We are putting in negative because iron is going to lose some of its heat. So heat is given by mc delta temperature, and even this side mc, but there will be negative mc delta temperature. What is the mass of the water? 20 grams water, so that is 20. Specific heat capacity for water, we know that is 4.184. Change in temperature is given by final minus initial. Now the initial is for water is at 25. Okay, and that is equal to negative. The mass for the iron is 30. Specific heat capacity is 0.48, and then final temperature we don't know. Then minus the initial is at 95. So if we multiply 20 times 4.184, 4.184, so that is giving me 83.68, and then T minus 25, and that is equal to negative 30 multiplied by 0.48. That is giving me negative 14.4 and then T minus 95. At this point, what I can do, I can even divide both sides by 83.68, even this side by 83.68. So I'll just remain with T minus 25 is equal to, so I'll just divide this value into this value because the whole of what is on top is the same thing. Okay, this is one thing, everything which you can see here is 1 because they are multiplying. So I'll just divide that value which is down into what I can see down. So I'm saying negative 14.4 divided by 83.64, I mean 68. So that is giving me negative 0.17208413, and then multiplied by T minus 95. At this point I can multiply this with what is inside. So what I'll get is T minus 25 is equal to negative 0.17208413 T, and then this value multiplied by the negative 95, it will become positive. So that will be positive 16.34799.235. So this one which has got a T, I'm going to take it over the other side, and then the 25 I'm going to take it over the other side. What I'm gathering is now the like terms. Okay. So if I bring this one this side, it becomes positive, it adds to the T. So it will be T plus 0. So T plus 0.17208413 T, it gives us 1.17208413 T, and that is going to be equal to, if the 25 goes this side, is going to become positive and it adds to that 16. So 16.34799.235 then plus 25. So that gives a value of 41.34799.235. So to remain with the T, I'm going to divide by 1. So 41.34 divided by 1.17208413. So that is going to give a final temperature of 35.2773246.3, which we can simply give as final temperature is going to be 35 degrees Celsius. Okay, so that will be the final temperature then. Another question, in a coffee calorimeter, 2 grams of sodium chloride was dissolved in 5 grams of water. So this is supposed to be water here, at a combined initial temperature of 23 degrees Celsius. So when we added the sodium chloride to the water, the initial temperature for the sum was 23 degrees Celsius. The final temperature was 25 degrees Celsius. So that is the final. Now I want to calculate the enthalpy of the reaction. Okay, how do we go about that one? So notice that what we have there is sodium chloride. This sodium chloride, after adding into the water, is going to dissociate into sodium ions and then chlorine ions. So now I want to calculate the enthalpy for this reaction, which is here. Now the only way that we are able to calculate the enthalpy of this reaction is, first we need to calculate the heat that is involved in this reaction. So let's first calculate the heat of the water. So heat of the water is given by mc delta theta. Okay, so the mass of the water have been given that 5 grams of water, so that is 5 grams. Specific heat capacity for the water is a constant value, which is 4.184 joules per gram degree Celsius. And then the change in temperature, it came from 23 to 25. Okay, so that means For us to reach at 25, what is the change in temperature? So delta T, which we can also call delta theta. So theta represents temperature. It's 25 minus 23, which will give us 2 degrees Celsius. 2 degrees Celsius. So that will be 5 multiplied by 4.184, also multiplied by 2, which is 41.84 joules. So if this is the energy that the water has, if this was the initial temperature and then this is the final temperature, that means that the sodium, the energy of the reaction from the sodium chloride is going to be equal to negative the energy of the water. So the same energy that water is going to release is the energy that the reaction is going to gain. If it is the reaction that releases energy, then the water is going to gain that energy. Okay, so the energy of the reaction is going to be negative 41.84 joules. So that will be the energy of the reaction in that case. Alright, now we need to find something here. We are given a certain, okay, we are told 2 grams of sodium chloride. So we need to find also the number of moles of sodium chloride which we have. So how do you find the number of moles? Number of moles is given by the mass over molar mass. So the mass of sodium chloride which we have is 2 grams. And then the molar mass, checking on the periodic table, sodium chloride. Let me just check through the periodic table to check the masses. So our sodium is 22.989, 23.98977. And then we are going to add the molar mass for chlorine, and our chlorine is 35.453. So that is going to give us a molar mass of 59.44277 grams per mole. So that will give us the number of moles of 2 divided by that value, which will give us 0.0336 moles. Okay, so those are the number of moles which we have found. Okay, now having found this number of moles, we need to perform a certain calculation. Okay, we want the energy of the reaction. So this is the enthalpy. The energy that we have calculated is simply the enthalpy. What is enthalpy? Enthalpy is simply the heat of the reaction. So delta H is simply equal to Q. That is the heat of the reaction which we can see. So what we are saying is delta H is negative. So let's just convert this value into kilojoules. So what I'm going to do, this value which I have is negative 41.84 joules. Now this is in joules per mole. Okay, so whenever we're talking about enthalpy, it is in per mole. As you can see, 1 mole of sodium chloride being broken into sodium ion and chlorine ions. So that is why we are saying per mole. Now what of these moles? Because the moles of sodium chloride present are less than 1 mole. So we're going to say if 1 mole is giving us negative 41.84 joules. What of these moles which you found? 0.0336 moles. What will be the energy? Okay, what will be the enthalpy? So I'll just say delta H. So I'll simply multiply these two. So that will give us delta H being equal to 41.84 multiplied by 0.33. Remember the 41 is negative. So the energy, the enthalpy is going to be negative 1.441 joules. But enthalpy is given is given in kilojoules, so we're just going to convert that value to kilojoules. So we are saying delta H is negative 1.41 joules. So we multiply, we have got a joule on top, so we're going to bring a joule down and then put a kilo on top. We know that in 1 kilojoule we have got 10 to the power 3 joules. So this joule is going to cancel with that joule. So that is going to give us a value of 0.00141 kilojoules. Okay, kilojoules per mole. So this will be the enthalpy for our reaction then. That becomes the enthalpy for our reaction, and it even ends here. Okay, that becomes the enthalpy for the reaction which we have. Now maybe another thing let's revisit is there's something that I've missed out here which we don't need to miss out. So just the heat which we calculated, which we are saying is in kilojoules per mole. Pardon me, this is not in kilojoules per mole. The heat which I found Q, which is equal to 41.84 joules. So this value is not in kilojoules per mole. Okay, I mean it's not in joules per mole. So we want first to take it in joules per mole. We want to, it is us who wants to take it in joules per mole for us to find the enthalpy. So the way it is at this point is just heat, it's not in joules per mole. So for us to take it per mole, then we need to divide by the number of moles which you found. And we found the number of moles from here. We said 2 divided by 59.44277. Okay, that was 0.0336 moles. So this energy is only in joules. So for us to take it in kilojoules per mole, for it to be enthalpy, we need to divide by the number of moles. So we are saying delta H, which is the enthalpy, is energy over the number of moles which you have found. So the energy is 41.84 joules divided by the number of moles, which is 0.0336 moles. So that will be 41.84 divided by the answer that you found. So that is going to be 1243.54 joules per mole. Now this is joules per mole. Now to take it in kilojoules per mole, of course this joules per mole you can also write as joule per mole. We write a mole down there. So we want kilojoules. So we are going to have a joule down because a joule is on top there. And then you are going to have a kilojoule on top. So in 1 kilojoule you have got 1,000 joules. So this joule and that joule cancels. And so then the value becomes 1.24 kilojoules per mole. So this now becomes the enthalpy of the reaction. Okay, the first one that you find from the reaction is not in kilojoules per mole. It's not in joules per mole. I mean, it's just joules. That's just the heat. All right. So let's take note of that. You shouldn't make that mistake. Now, question 6. Calculate the energy required to heat 24 grams of ice at negative 20 degrees to steam at 200 degrees. So what we have first, let's consider this. So this will represent the temperature. This will represent the heat that we are supplying. So if you have got ice which is at negative 20 degrees, let's say negative 20 is here. This ice first, we need to raise the temperature. We are supposed to raise this temperature up to 0 degrees. And what is involved here is heat capacity. Okay. Heat capacity, the amount of heat energy required to raise the temperature of a substance. So we've raised the temperature from negative 20 to 0. And then when it reaches 0, there will be a change of state that will be happening. So we are converting now the ice to water. So after we've converted all the ice to water, so we are going to have the first energy here, Q1. And then we are going to have another energy here. So this Q1 is the energy required to convert from negative 20 to 0 degrees. And then we are going to have Q2, which is required to convert now the ice which is at 0 degrees to water at 0 degrees. Okay. So if we have got water at 0 degrees, we'll start raising its temperature. When we reach 100 degrees here, the temperature will stop changing. So this Q3, this is the energy required to convert the water from 0 degrees to water at 100 degrees. We are just raising the temperature of the water. And then after that, the water will start converting. Will start converting from water into gas. When all the water is converted into gas, the energy involved there is Q4. And then now, the gas will now, the temperature will start rising up to now the wanted 200 degrees. And that will be Q5. So these are the energies that we are going to spend 5 energies. So let's first calculate Q1. Q1, the energy required to raise the temperature. Rising the temperature of ice, whenever we're talking about raising a temperature, is specific heat capacity. So we're going to use MC delta T. The mass of the ice at that point is 24 grams. And then specific heat capacity of ice, where have we been? The heat capacity, okay, the specific heat capacity of ice is that one, 2.03. Okay. And then what else have we been given? The change in temperature. For the specific heat capacity, this was supposed to be joules per gram degree Celsius. Even this was degree Celsius. The specific heat capacities. Okay. And then change in temperature. We are moving from 0 up to, we're moving from negative 20 up to 0. So change in temperature, the final temperature is 0. The initial minus the initial is negative 20. So the change in temperature here will be 0 minus negative 20, which is simply 20. So that will be a 20 there. So 24 times 2.03 times 20, that will be 974.4 joules. What of Q2? Now, what is happening is there is a change of state. Whenever there is a change of state, what is involved is latent heat. Now here it is latent heat of fusion. When we want to convert a gas, a solid to a liquid, is latent heat of fusion, which is given by MLF. LF is representing latent heat of fusion. So the mass is not changing, it's still 24. Now the latent heat of fusion we've been given, the latent heat of fusion of ice is 334. So if we multiply this, we are going to get 80.16 joules. What of Q3? Third energy. The energy required to raise the temperature. Whenever we are raising the temperature, what is involved is specific heat capacity. So it will be MC delta T. The mass doesn't change anyway. Okay. The mass is still 24. Specific heat capacity. Now what we have here is no longer ice, but it is water. Specific heat capacity for water is 4.184. Then the change in temperature, moving from 0 to 100. The final is 100. So the change in temperature will be final 100 minus initial is 0. So that would be simply 100. So 24 times 4.184 times 100, that gives us 10,041.6 joules. Let's also find Q4. Now see, at the fourth energy there is a change of state. Whenever a change of state is happening, what is involved is the latent heat. But because here something is vaporizing, it's changing to vapor, is latent heat of vaporization. So the mass is still 24. Okay. Now the latent heat of vaporization, where has it been given? Latent heat of vaporization has been given as 40.7, but it is in kilojoules per mole. Okay. Now remember what you have here, so we need to be very careful with the units. What you've been given first is the mass from the formula. Mass is in grams. and then multiply by the latent heat of vaporization has been given as 40.7 kilojoules per mole. So the first thing that we want to do is we need to convert this so that you'll be able to cancel with what we have. 40.7 kilojoules per mole. So the first thing, we need to convert this because we want to cancel with that gram. How do you convert that mole to gram? Anyway, let's not convert the mole to gram. Let's keep it the way it is. But let's just convert the kilojoules into joules. So we're going to multiply. I've got a kilo on top, so we're going to bring a kilo down. And then we're going to have only a joule on top. We know that 1 kilojoule is equal to 1000 joules. So this and that is going to cancel. So that is going to give us then 47, then 00 joules per mole. Now we can convert this mass of water into moles. So that is 24 grams of water. How do we convert the 24 grams of water into moles so that the units are going to cancel out properly? So number of moles is given by mass over molar mass. The mass we've been given 24 grams of water. And then the molar mass has been given as what? So the molar mass has been given as, okay, the molar mass for water is 18 grams per mole. So 24 divided by 18, that is 1.33 moles. Actually, what we are going to have, what has been given here is the molar heat capacity. And molar heat capacity, how do you find the molar heat capacity? Okay, heat of that is the molar heat of vaporization, not heat capacity. This is heat of vaporization, but it's been given as a molar. That is because we've used moles. And so the formula changes slightly. Instead of using mass, we're going to use number of moles, because what you've been given is the latent heat of vaporization in terms of moles. So the number of moles we found 1.33 moles, and then multiply the latent heat of vaporization now is this one here which we've converted, and that is 4700. It is now in joules per mole. Notice that the mole is going to cancel with the mole. So multiplied by 4700. So now that is going to give us 54266.7 joules. So we have found Q4, and then lastly let's find Q5. And how do you find that Q5? Remember, we are raising the temperature from 100 to 200. So raising a temperature, what has to is about specific heat capacity. So that will be mass, specific capacity, and then change in temperature. The mass has been given as, anyway, the mass is still the same as 24. Specific capacity, now this is vapor. Remember, we've already converted. It's no longer water. After exceeding this point, what we have here is not water, it's vapor. So the specific heat capacity of steam, okay, is 2.01. And then the change in temperature, the final temperature is 200, the initial one is 100. So 200 minus 100, change in temperature is 100. So that is going to give us 24 multiplied by 2.01 and then multiplied by 100, which gives us 4824 joules. So to find the total energy, then the specific heat, calculate the energy required to heat. So whenever we want to heat, when we want to heat negative 24 grams of ice at negative 20 degrees Celsius to steam at that temperature, the energy change is going to be the sum of all these energies. So the energy will be Q1 plus Q2 plus Q3 plus Q4 plus Q5. So I'll start adding them. I'll start with the last one, 4824, and then I go to this one plus 54266.7, and then plus I go to this one, the third one, which is 10,041.6, and then plus I go to this one, which is 80. Oh, sorry, not that one, there's no value there. Where we're going is to this one, Q2, which is 80.16, and then I go finally to the first one, which is 974.4. yes. Okay, 80.16, and then plus we are saying 974 plus 4. So therefore the heat or the energy that is going to be required is 78,122.7 joules of energy. So this is the energy that is going to be required for us to convert ice at that temperature to steam at also that temperature. All right. So we have got another problem here. When 1 mole of methane is burnt at constant pressure, 890 kilojoules of energy is released as heat. Want to calculate the enthalpy in which a 5.8 gram sample of methane is burnt at constant temperature. Okay. So the first thing we need to find is, of course, we already know when 1 mole of methane is burnt. So 1 mole being burnt, the heat that is going to be released is 890 kilojoules. So this is telling us that the enthalpy when 1 mole is burnt is negative 890 kilojoules. So that is per mole. So this is the energy that is released per mole. Just the word release, that's why we are putting a negative there. Now what if we burn 5.8 grams of methane? So first need to determine the number of moles. So the number of moles, we know this mass over molar mass. So the mass we've been told 5.8 grams. And then it's methane. The molar mass for methane is 10.04 grams per mole. So that is going to give us 0.36 moles. Okay. So let's consider this enthalpy. Delta H, we know that it is negative 890 kilojoules per mole. Since we have got a mole down, we are going to multiply with this mole, which is here, which is the 0.36 moles. Notice that a mole and the mole is going to cancel. Then we are going to have negative 320 kilojoules. Okay, so this will be the, what is the question even? Calculate the change in energy. So this will be the change in enthalpy. See the change in energy. If we didn't want to use this one, we could just pick it from this point. We say 1 mole is producing it's producing 890 kilojoules. The negative is simply representing producing. What of the moles that you found? 0.36 moles. How much are they going to produce? So this will still give us the same value. X is going to be the product of 0.36 by negative 890, which is still negative 320 kilojoules, the same value. Alright, last question then. We've been given when 1 liter of 1 molar barium nitrate solution at 25.08 degrees Celsius is mixed with 1 molar, 1 liter of 1 molar sodium sulfate at also 25 at the same temperature in a calorimeter. What you are going to see is a barium sulfate which is formed. Okay, and the temperature. So the temperature of the mixture increases to 28 point. So at the start, both of them are at the same temperature, but when you react them, so what you are saying is a barium nitrate. When we reacted it with a sodium sulfate, what we produced first was this precipitate, a white precipitate, which is barium sulfate. Of course, we are going to have another product, which is in this case it will be sodium nitrate. Okay, that will be the other product. Now our interest is only in the precipitate. How did we produce this precipitate? So the ions of barium reacted with the ions of sulfate to produce that. So barium 2 plus reacted with the sodium 2 minus to produce the barium sulfate. Okay, that is a precipitation reaction. The other ions were spectator ions, are going to cancel out. Okay, if you want to determine how they cancelled out, let me show that so that we see. We have got barium, all these are in aqueous. This is in aqueous, this one is in aqueous, this is a solid, this is also in aqueous. So the barium is going to dissociate into ions, so it becomes 2 plus. Okay, is this a balance equation? We're going to put a 2 there to balance the reaction. Okay, and then plus the nitrate is also going to dissociate. Notice that there is a 2 there, so that 2 comes in front, NO3 minus, so a nitrate is negatively charged. And then the sodium, notice that there is a 2 there, that 2 comes in front, so 2 sodium plus, and then a sulfate which is SO4 2 minus, that will produce barium sulfate. Solids don't disassociate, so that remains like that. And then we've got 2 sodium ions. This 2 also applies to the nitrate, so we also have 2 nitrate ions. So we're going to cancel out spectator ions, those which are appearing on both sides. So those are the ones which are appearing on both sides. And so what remains is the barium 2 plus and also sulfate minus, producing the barium sulfate. Alright, so this is what we have. Okay, now starting from here, assuming that the calorimeter absorbed only a negligible quantity of heat, that means the calorimeter itself, where the reaction happened, we take it as if energy wasn't lost. Okay, so the specific heat capacity of the solution, so they are occurring in a solution of water, and so we are using the specific heat capacity of water, and also the density of water also, which is 1 gram per milliliter. Now I want to calculate the enthalpy change per mole of barium sulfate. So this is the enthalpy of formation, because we are forming barium sulfate. Or we can also call it as the enthalpy of precipitation, because we are forming a precipitate. Alright, so now how do we go about it? The first thing that we want to determine is, let's find the mass of the solution. Okay, so the mass of the solution. So the mass, how do we find mass? Now we've been given the volume. We are told 1 liter of this reacted with 1 liter of that. So we have got 1 liter here reacting with 1 liter there. So the total volume is now 2 liters. And then we've also been given, what have we been given here? We've been given the density here of the solution. So the density of the solution has been given as 1 gram per milliliter. So we can simply convert. Of course we know that density is mass over volume, but what we want is the mass. So that will give us mass to be equal to density times volume. So we're getting the density, which is 1 gram per milliliter. And then we are multiplying by the volume. Now that's the volume of the solution. Remember, the solution was made up of 2 things, so the volume is the total. So that will be times 2 liters. Now notice that we have got milliliters here. They can't cancel with the liters, so we need to convert those milliliters to liters. So we're going to multiply. Because the milliliter is down, we are going to put a milliliter on top. And then we're going to have a liter down. In 1 liter we've got 1,000 milliliters. This liter, notice that it will cancel with this liter. The milliliter cancels that milliliter, and then we are going to have now our grams. So that will be 1,000. I mean 2 times 1000, it will give us a 2000 grams. So that is the mass of the solution. After finding the mass of the solution, let's determine the change in temperature of the solution. Now the whole solution, this one was at the same temperature, the other one was at the same temperature, but both of them, after they were reacted, the final temperature increased to 28.18. So the change in temperature will be equal to the final, which is 28.18, subtract the initial, both of them were at the same temperature, 25.08. So that is going to give us 3.1 degrees Celsius. That is the change in temperature. Okay. So we know the mass, we know the change in temperature. So remember, the question is calculate the enthalpy of change. So the first thing we need to calculate is the energy, because if we know the energy or the heat, then we can easily talk about the enthalpy. The heat of the reaction. What is the heat of the reaction? So heat of the reaction is given by mc delta theta. Okay, we're going to use the standard, the specific heat capacity, I mean, for water, because talking of the solution was the solution of water. So the mass is going to be the same mass which we have here, which is the 2000 grams. Specific capacity is 4.184 joules. Okay, this was supposed to be degrees Celsius and then gram. So the unit for specific heat capacity is joules per gram degree Celsius. That is what should be collected on that point. And then times the change in temperature you've seen as 3.1 degrees Celsius. So the degree Celsius cancels with this degree Celsius. Okay. Notice that this gram is going to cancel with this gram. So our energy is going to remain, or our heat is going to remain in joules. And that is going to give us 2.6. Let me just repunch on the calculator. We are saying 2000 multiplied by 4.184, then multiplied by 3.1, which gives us 25940.8 joules. So we can convert this to kilojoules by multiplying. We know that we have got a joule on top, so we're going to put a joule down, and then we can put a kilojoule on top. We know that in 1 kilojoule we have got 10 to the power 3 joules. So notice that the joule is going to cancel with that joule. So that then gives us 25 point, okay, that is 25.9408 kilojoules. Alright, so that will be it. I can also round it off as 26 kilojoules. Now, if we've been given the mass of the precipitate which was formed, we haven't been told the mass of the precipitate that was formed. So we take it as one more of the precipitate was formed. Okay. So that is the amount of energy, of course, that is going to be involved in this reaction. And so we want to calculate the enthalpy. So delta H then is going to be equal to the heat divided by the number of moles. So the heat which we have is 26 kilojoules, and then divided by the number of moles. We are talking of 1 mole, because the question is calculate the enthalpy change per mole. So that will simply give us 26 kilojoules per mole. So that is the enthalpy change in this case. Alright, that marks the end of this video. Hope it was helpful. Thank you so much for watching. Stay blessed.